In this video, we're going to talk about volume charge. This process can be fairly complicated, but as we will see later on, it can be greatly simplified using Gauss's law. So starting off, we know that the total charge Q is equal to the volume integral of the volume charge density. Now we're going to assume that the charge density is constant, so we can pull it out of the integral. The volume integral is simply the volume of a sphere. Now if you look to your right, you will see the geometric setup of this problem. The little box represents the differential amount of volume charge, and the vector capital R is the distance from that little volume to the point of interest. So the differential amount of electric field is given by Coulomb's law. The unit vector A sub r can be written like this. You should verify this yourself though from the geometry to the right. Because of the symmetry of the sphere, the electric field coming from one side of the sphere will be cancelled out by this field coming from the opposite side of the sphere. Thus, the field has no rho or theta dependence. Now because of this, the only component that isn't cancelled out is the z component. Thus we can write the integral like this. Now we're going to be using the spherical coordinate system. From vector analysis, we know that when we change variables, we need to introduce the Jacobian correction factor. This is given in the formula for dv. From the law of cosines, we can get relationships for r and capital R. You should verify this yourself, however, from the geometry. We will now solve each relationship for cosine. Now we want a relationship for sine since it will be in our integral from the expression for dv. We will get this by differentiating cosine theta with respect to theta. When we do this, we will keep r and z constant because we need only theta dependence to get a d theta. This might be a little confusing at first, but is the only way to get a relationship we want in the Jacobian correction factor. We now plug all these relationships into our original integral and we get the following. Well, it looks like a real mess. So let's do this one step at a time. The integrand has no phi dependence, so we can evaluate the integral with respect to phi and simply get 2 pi. We now cancel out the 2's and do a little bit of algebra to simplify things up. Notice that I did not cancel out the pi's. You'll see later why I've done this. We evaluate the integral with respect to capital R and then with respect to little r. When we do this, we can rearrange things using the pi from earlier to get an expression for total charge. We now have our final expression for the electric field. We can replace the z with an r since z represents the distance from the center of the sphere. Notice that this is the expression for the electric field of a point charge. Thanks for watching everyone. Be sure to rate, comment, and subscribe.